Assalamu alaikum, sir. I am Juhair Ranab Jihan from the Department of Computer Science and Engineering. Today, I am very excited to present our project report on empirical time complexity and friendship graph simulation. And here are my teammates, Sumaya Jannat, Sumaya Hussain Alifa, and Tashfiya Asha. So let's dive into the fascinating world of algorithms and graph theory. So here is the outline we'll cover today. In part one, we will explore the empirical time complexity of linear search and compare it with its theoretical counterpart. In B1, we will simulate a social network using an undirected graph analyzing key properties like vertex degrees and connected components. We will wrap up with our conclusions and theory to practice. Um, Moving forward, for part A1, our objective was to determine the empirical time complexity of linear search and see how it stacks up against theoretical complexity. We wanted to measure how the algorithm performs in practice and confirm whether it aligns with the expected O and behavior. Um, In the methodology part, we implemented linear search in Python. We generated random arrays ranging from 10,000 to 50,000 elements. For each array size, we conducted 1,000 searches for random targets and recorded the average search time in milliseconds. These results were then plotted against array size with a trend line to visualize the relationship. Here are the results. Mm, Average search time versus average search time versus array size. This graph shows the search time plotted against array size. The linear trend is clear, indicating that as the array size increases, the search time grows proportionally. The trend line closely follows a straight line supporting our hypothesis. The results show that the average search time increases linearly with the input size n, confirming the empirical time complexity of Tn equals to On. This matches the theoretical average case complexity of linear search, demonstrating a strong alignment between our experimental data and algorithmic theory. Moving to part B1, our goal was to simulate a social network using an undirected graph. We aimed to analyze key graph properties, including vertex degrees, the handshaking theorem, and the number of connected components to understand the structure of the simulated network. We generated adjacency matrices for graphs with 500,000, 1,500, 2,000, and 2,500 vertices, representing users in the network. Friendships were randomly created with a probability of 0.01. We computed the degree of each vertex, verified the handshaking theorem, where the sum of vertex degrees equals twice the number of edges, and identified connected components using depth first search. Here are the results. This graph illustrates how the number of connected components changes with the number of users. As the graph size increases, we observe fewer connected components, indicating a more interconnected network. Our simulations verified the handshaking theorem across all graph sizes as the sum of vertex degrees consistently equaled twice the number of edges. Additionally, larger graph produced fewer connected components aligning with graph theory expectations. This suggests that as the network grows, users are more likely to be part of a single larger connected community. To wrap up, our project successfully bridged theory and practice. For part A1, the empirical results confirm the Owen time complexity of linear search, matching theoretical predictions. For part B1, our friendship graph simulation validated the handshaking theorem and provided insights into connected components. Together, these experiences highlight the power of empirical analysis, reinforcing theoretical concepts. Thank you so much for your attention, sir. We are happy to answer any questions.